Well, thank you for that introduction. It was a lot more detailed than I was expecting. I hope that I hope that um, I can live up to those expectations here. So first of all, I know I can't see your faces or names, but I'm very happy to give this presentation and to know that some of the people who worked with me in the field in Southeast Asia will be listening to it. And I'm working hard to finalize some of the results, as I'll talk about, to publish them. And many of the people listed on the screen here will be co-authors, and I will be seeking your input once we finish pulling all the material together. Um, what I'm going to do is to focus on the field schools and give you some results. And I was asked also to focus on map making, which was a critical part of the field school. So you'll see a lot of that. Let's see. Advance this. Okay. As you all know, the plate tectonic situation in Southeast Asia is driven by the Indo-Australia plate. I hope you can see my pointer. India and Australia are being shoved into Asia. You can see all these earthquake belts in through here. And of course, we're most interested in the area right here in Western Southeast Asia. In a more cartoon view, you can see that as India goes into Asia, it's effectively squeezing out much of Southeast Asia here. And remember, Australia is impinging from the south as well. It's also squeezing out a large amount of China, particularly along the Altantag and other faults. And it's now starting to break off even more of Asia, including the Tian Shan, where I've worked many years with my collaborators from Kyrgyzstan. So to understand the earthquake hazards, we generally want to know what the strain is. So I show you a couple of published results of the strain. The one on the left that I'm pointing at is the release rate of strain. So when earthquakes occur, they release strain. And so we can map out the release of strain. And as you can see here, it's the boundary between India and Asia. And also the Sagaing Fault is releasing strain at a very high rate. We can also look at the accumulation of strain, and we use GPS to look at the accumulation of strain. And here's a map of the GPS stations that were used in this study to look at this. And as you can see, there are many, many sites along the boundary in northern India and southern Tibet as well. Also, China has many, many stations. There are many, many stations in the Tian Shan and the Pamirs, again, because of the projects that I've worked on with other people in Kyrgyzstan as well. And this produces a map of strain accumulation that's very much like the map of strain release, with the boundary in front of the Himalayas and the Sagaing faults showing up, but also faults in China like the Xuanzhuihe fault and faults in the Tian Shan and in Central Asia as well. If we make a map of hazard, and usually hazard is expressed as peak ground acceleration, PGA, in some interval, usually 50-year probabilities, we see, based on the strain rate or based on the GEM model, quite a difference, especially in Southeast Asia. And for reference, about damage, significant damage starts to occur at about 0.1 G. So somewhere in this color here. And then, of course, severe damage when you get above 1 G. If we look at these for Southeast Asia, we see a big difference. And in fact, I care a lot about this big difference because I have one sister and her family in Chiang Mai, which is here, and another sister and her family in Chiang Rai here. And you can see the difference in this area is incredible, largely due to the lack of earthquakes in recent times and the lack of GPS, and again, the lack of studying the geology. So I've been working largely with the Earth Observatory of Singapore to try to improve these regional scale hazard models. And the short of it is we need longer records, and those are only going to be available in the geology. This figure shown here is a preliminary seismic hazard map produced by colleagues at EOS. And we will be focusing on the Sagaing Fault, and I'm going to also show you a little bit on the Nam Ma and the Mechan faults in this area as well here. Okay, so field schools. The Earth Observatory of Singapore, and especially Shi Hua and Wang Yu, who were postdocs there when I first started going in 2015, they gave me some money, and Carrie C., who was also, as you heard, my advisor at Caltech, directed some student education money from the Sloan Foundation to do this. The Thai DMR, especially when we worked in Thailand in 2017, contributed. The University of Oregon contributed. They gave me 5 years of teaching release, and they paid for travel and scholarships for 4 US students. Oregon State, California Geological Survey, Portland State, basically my ex-students who teach now or work at state organizations came and helped, and China supplied support for students from China. We covered paleoseismology, which we'll talk a lot about, collection of samples, making maps and mosaics that I'll talk quite a bit about as well, mapping faults, GPS, drone, ground-based LiDAR. I particularly like this picture, which is one of our exposures at the Sagaing Fault that I'll talk about later, because as you can see, all the long hair, see all the long hair sticking out back here? In our classes, we had 50% female and 50% male. We had students from 11 countries, most countries of Southeast Asia, and American and Chinese students. Except for a similar teaching school that I did in Kyrgyzstan, I don't know of any other international collaboration of this sort. And so I'm very excited and proud of it in addition to the results. And I look forward to learning about what has happened to many of these students. I know some of them went to school in foreign places and have done well. Okay, the first thing we start with is we make a map. And usually we use a drone or stereo air photos. And for the project on the Sagaing Fault, we use this drone that Wang Yu is showing off here. And if you look at this later, you can click on these YouTube videos and actually see videos of a lot more of the fault than I'm going to show you here. So drones are tremendously useful in this kind of work. If we look at this, we can see the Sagaing Fault. Now, I hope all of you can see there is a fault here, right? Right down the middle. Okay, good. Notice how the drainages are blocked by the fault or offset by the fault. You can see, for example, this fairly large drainage came from this stream originally, which has captured these other streams. This large canyon probably came from here. Also notice that the valley floor is uplifted in this area as well. And finally, just sort of for scale, if you have been in this area, this is a road up to the temples here to give you a sense of the scale here. So we chose to trench a site where the fault appeared to step. So Wang Yu did a preliminary map of the fault zone here and picked this area for us. It's about 4 kilometers northwest of Mandalay. It's near Yikar Lake and Yikar Village. And there's a small valley in here, and I'll explain why we chose this spot. Again, we use previous UAV that he flew to study the fault and combined it with drone imagery, ground-based LiDAR, which is very useful for removing the vegetation, as you can see. And then we made really excellent maps here. And again, you can see, for example, a nice scarp here on the range front. You can see a beautiful beheaded stream. This stream used to come out of here and has now been beheaded by the fault that goes through here. But you can also see the uphill facing scarp. You can see this fault scarp through here. These are higher areas blocking the drainage coming out of the mountains. Now, before I talk about the earthquakes here, I want to show you how we've made maps in other places in Southeast Asia. Because as a field geologist, making maps is tremendously important. And many of the students that I've taught, they have gone on and made incredible maps of places they've worked. So let me show a bit more in the map making, and then I'll return here. If we return to our index map here, remember you have the subduction zone offshore. Well, that's pretty hard to study, at least from the ground. We've been looking at this area on the Sagaing Fault here. And then there's these faults in the area of Myanmar, Laos, and Thailand that are due to the rotation and extrusion of material from behind India here. And so let's look at these here, and I'll show you some maps we've made in these areas, and then we'll return to the Sagaing Fault. If we look in the Golden Triangle region here, so here's the Mekong River. So this is Laos, Myanmar, and Thailand here. And we have a series of faults that produce earthquakes. Jinghong that we've worked on a bit, the Nam Ma and the Mechan faults are the ones we've studied. And in 2011, there was an earthquake on the Nam Ma fault that produced this red offset of about 30 kilometers or so here. So a couple of points I want to make here. One is smaller earthquakes don't make surface rupture. So for example, this earthquake of 6.3 on the Mechan fault did not make a surface rupture. Generally, you have to be greater than 6.5 to have rupture. That varies in places, but that's a general rule. But once you get to something like 6.8, you see a significant rupture here. And instantly, after the rupture, you can see it along the ground. Now, I didn't draw that. That's just Google Earth. You could just zoom in or could have zoomed in and looked at it immediately after the earthquake here. And I'm going to zoom in here in the next picture. And here you can see nicely the surface rupture and the offset to the left of all of these rice paddy boundaries, as you can see here. And the fault zone is quite narrow, about twice as wide as the boundary of a rice paddy. If we go look on the ground, again, you can see the curved area. So this area has been folded and this area has been faulted. You can see it's mostly curved and folding in here, as you can see. If you look down the fault, you can see nice fractures forming. You see these fractures breaking up features like this. You also notice the water on one side, both here and here. And once you start looking, you can see this side came up relative to this side. Now you can imagine in past earthquakes, similar things would happen. So we look for a place where we can find these things, and here's where we decided to work. So in this case, there's an alluvial fan that's shedding sediment down here. There's another alluvial fan that's shedding sediment down here, and it's piling up against the fault running through here. And you can see this was in 2017, so only 6 years after the earthquake, that beautiful fault scarp is already buried. And so if it buried the 2011 rupture in just 6 years, then older earthquakes will also be buried here. And this is the concept of paleoseismology. And so as you can see, we dug trenches here, and here's our students working hard, as we can see, working on these trenches, looking at the earlier earthquakes. A couple quick examples as well. We can also make maps from old air photos. This is from Thailand along the Mechan Fault here, from very old air photos that we got out of a museum. And the fault zone here takes a lot of steps. You can see the fault is here, and then it steps over to here, and now you can see it's starting to step to here. And so we can see what it looked like before development, and I want to zoom into this area here. If we look at this area here, we can see these streams with these nice left lateral deflections, just like the rice paddy offsets, but much larger. But if we look at Google Earth today, it's very hard to see these things. So for example, this reservoir here was built by putting a dam here and making a lake. This reservoir here was built by putting a dam here and making a lake. If we zoom into this area here, note the road and the houses. Here's the road again. Here are the houses. We can put the topography, the brown lines are made from the 1945 air photos, and we can see how things have changed. These hills were smoothed out to make the houses. All of this dirt was dug out to make the dam for the reservoir, which you see here. And so you can see how valuable it is, particularly in areas with development, to look at the oldest things that you can to understand what's happening. Okay, one more example, I think, and then we'll return to the Sagaing. This is one of my favorite places on the Mechan Fault near the Banpangsa. And there's a debris flow that flowed down out of a side canyon here. And if we look at it here, the fault is running through here like this. The debris flow comes out to the fault here and has been offset to here. See all these boulders that you see on the debris flow. And we didn't need drones or air photos to work here, we just use photographs. So we do this as well. What we do is we locate a few spots with GPS. Often we put like some rods on the ground that point north that are a meter long. And then each of these blue places are where we took photographs. So we just walked along and took photographs here. Then we walked up the hill and took photographs here. And then we put them together into this 3D model. So you can do this in places where you have some topography, even if you can't fly something here. And again, notice where the fault crosses. Notice how the edge takes this bend here. It's the same as this bend here. And to quickly summarize this, this is an offset. There's a small terrace that we cleaned off later. You can see the break and slope here that we dated at 3,000 years about ago. And it has been offset from here to here about 4 meters, we think, by the 500 AD Wyangyonok Nakhon earthquake, a historic earthquake that destroyed Alana Kingdom. We took samples from the boulders and did cosmogenic dating to get 17,000 years old. And now we have a slip rate of 1.7 or 1.4 millimeters a year. Again, we made the detailed map just by walking around and taking pictures. Okay, let's get back to the Sagaing Fault and the Sagaing Fault trenches here.